Inverse hyperbolic functions is next. So let f of x equal sinh x. And we'll show this for sinh. For cosh, you have a little more to do because you need to restrict the domain because cosh basically looks like this. So you got a strict domain for cosh. Sinh, though, is that. So you essentially, this will be true for its entire domain, which I'm getting to now. But we'll just do this for sinh. F, so I'm defining f to be sinh. So f is continuous and increasing it's e to the x plus e to the negative x, so it's always increasing for x in the reals. Therefore, so if that's the case, it's basically monotonic, then continuous monotonic, then it's one-to-one. So for x in R, its domain, therefore f is one-to-one. And if it's one-to-one, we know f inverse exists. Or we can say sinh x inverse. I put that in the wrong spot. Sinh inverse x exists. So we want to find an explicit form for sinh inverse. So find an explicit form, basically in terms of e to the x exponentials, how it's defined. Okay, so what we have then is we're going to set y equal to sinh inverse of x. And because of above, that's equivalent to if and only if x is equal to sinh y. So we can write that as a definition. So x is equal to sinh y, which is equal to e to the y minus e to the negative y over 2. So let's multiply both sides by 2, and I have this form. This is just simplifying stuff. So it's 2x equal to e to the y minus e to the negative y. Now, let's set this equal to 0, and you get this equal to, if and only if, e to the y minus 2x minus e to the negative y is equal to 0. So what we're going to do is we're going to multiply on both sides by e to the y, right? Because that's a positive number, and you have an equation, so you can multiply either side by whatever you want, as long as it's non-zero. So when you get that, we have e to the 2y minus 2x e to the y, and then this becomes just 1. So you have e to the y here, then that adds to be 0, and you get 1. Okay, so what this is, do you recognize that form? This is quadratic form. And we can let my u be e to the y. And if you do that, you get u squared minus 2xu minus 1 equal to 0. And we can solve that using the quadratic formula, where you have your a, this whole thing's your b, and your c. So you say u equals, but u is e to the y, so we'll just put it in there like that. So we'll say e to the y is equal to minus b, so it's 2x plus or minus the square root of b squared minus 4ac. So it's 4x squared, and then this becomes a plus because it's 4ac, so it's a plus in the middle. Okay, all over 2a, which is just 2. All right, so we simplify that, factor out the 4 and stuff, and simplify it. So you get 2x plus or minus the square root of 4x squared plus 1 all over 2. And then we can see here that this 2, and when you do square root of 4, you get 2. So that will reduce out. And then you have, so this is equivalent to, if and only if, e to the y is equal to x plus or minus the square root of x squared plus 1. So we basically have these two possibilities. We have x minus root x squared plus 1, and we have x plus the square root of x squared plus 1. So we can argue that this one always has to be positive because you have a 1 and everything else is positive. And similarly, this has to be negative. So this is less than 0. And so we need to throw out the negative case. But why? Why do we throw out this case? Because e to the exponential is always positive. So we have that. So e to the y is greater than 0 for all y. So we have then e to the y must be the positive case. X plus the square root of x squared plus 1. And how do you get y down from there? What do you do? So you do ln on both sides, right? So you take the natural log on both sides, so you get y is equal to the natural log of x plus the square root of x squared plus 1. But what was y defined to be originally? Y was defined to be sinh inverse x. That's how we started. So that is sinh inverse. So sinh inverse of x is equal to ln x plus the square root of x squared plus 1. So a lot of stuff in this derivation that brings up quadratic form to solve, natural log on both sides, right? Solving for inverses. So there's a lot of good stuff here. Analyzing the function for extraneous. Okay. All right. So next, a couple more things. Let's just do a couple derivatives, and that should wrap it up. Okay. So we want to look then at the derivative of that. So let's see. Let's just do it here. So let's here, let me just write it like this. Derivative of sinh inverse. That's basically what I'm going to do. So we're just going to work it out. So dx of sinh x, or sinh inverse x, is equal to ddx of the natural log of all of that. So it's x plus the square root of x squared plus 1. Like that. Now when you do the derivative, you must use chain rule. So apply chain rule. And so you get that this is 1 over all of that. So this is equal to 1 over, this is the derivative of natural log, is 1 over x plus the square root of x squared plus 1 times the derivative of what's inside. So the derivative of what's inside is derivative of x is 1, and then plus, and then that'll be the 1/2 x squared plus 1, and then chain rule again to the negative 1/2. So then it's times your 2x, which will simplify and reduce a bit. So that's equal to, so now let's just start simplifying this. So you get 1 over x plus the square root of x squared plus 1. And this becomes 1 plus, so the 2's are gone. You end up with just x over square root of x squared plus 1. And so now we just need to add rational expressions. Well, they're not really rational, right? I mean, they're expressions. So add the fractions, basically, these common denominators, and add them up. So we add these together first, and we get this is equal to all of the first one. So it's 1 over x plus the square root of x squared plus 1. And then this will be x, sorry. All right, so you need to multiply by this top and bottom, and then add that up. So you end up getting the square root of x squared plus 1 plus x all over the square root of x squared plus 1. Like that. Now check out what just happened. This is what's kind of cool about it. Look at this and this are the same. So the whole thing's gone. So that's just equal to 1 over the square root of x squared plus 1. No need to rationalize or anything. I mean, you would just get root x squared plus 1 over x squared plus 1. So it's actually in some ways more complicated if you try to rationalize. So that is the derivative of sinh x. So now let's apply that. And so if y is equal to sinh inverse, put that the right way. So if y is equal to sinh inverse of, let's just say tangent x, find y prime. So now you just apply the chain rule using this. So what goes down here, really? That's your question here. So y prime is equal to, so now the derivative of sinh is that form. So you get now 1 over the square root of, but then this needs to be tangent squared x plus 1. And so now we can apply an identity for tangent squared x plus 1. So one of our identities is that. So look that up if you don't remember. Tan squared x plus 1 is secant squared x. So you can write that as the square root of secant squared x. And the square root of the square is just absolute value. So it's absolute value of secant x. But you can always do absolute values like the whole thing, because this is just a 1. and flip the secant, which becomes cosine. So this is just absolute value of cosine x. So a lot of this will work out nicely, some messy. You'd have to see. Okay, that finishes up chapter 7.